Hello again, everyone. This is chapter 6.6, where we'll be discussing inverse trigonometric functions. Now, first, let us recall exactly when a function has an inverse, and it's only when the function is one-to-one. So here I say recall, a function f of x has an inverse function, f inverse of x, only when f of x is one-to-one. In other words, it passes the horizontal line test. Now, cosine and sine fail the horizontal line test tremendously. There is something to kind of note here, though. So I'm going to talk a little bit about domain and range for a second. And if you recall from inverses, domain and range of an inverse function is the opposite way around. So if the function sine of x has a certain domain and range, its inverse, if it has an inverse, would have opposite range and domains. But we'll see that shortly. So I'm going to talk a little bit about the domain and range for each one of these. The first thing to notice, I think, is that the range is the set of all outputs. The highest an output can be is 1, and the lowest it can be is -1. So that means the range is actually the y shadow, -1 to 1 inclusive, because it could be equal to -1 and 1, of course. Now the domain, as is here, is actually, well, -infinity to infinity. You can plug in any x value into sine, and you'll get a y value. But what we want is we want the domain so that an inverse function actually exists. In other words, we want to restrict our domain so that the function is not failing the horizontal line test. So there's actually a few different ways you can do this, but the standard is to do the following. We're going to make cuts here and here. So if we only focus on this, so I'm going to erase everything else here. And you kind of see why, because if you go a little further down beyond the red point that I drew here, that's when we start to fail the horizontal line test. Similarly, if you go to the left of this point here and go above, that'll be where you start to fail the horizontal line test on that side. So this is one section of the graph of sine that actually, it satisfies sine being one-to-one in this domain. So this restricted domain now is in between -π/2 and π/2, inclusive. So that's what we're going to work with. It's a pretty important concept, actually. And we'll see that come into play in a second. Same thing for sine. Well, if you look at sine, right here at this point is where we have this curving feature where if you go a little bit beyond this point, it'll fail the horizontal line test. If you erase pieces of the graph at that point, and similarly to the right of this point, now this subsection part of cosine actually passes a horizontal line test and is then one-to-one. So here, the domain restriction is actually different. It's not -π/2 to π/2, it's actually 0 to pi. And again, these are all closed. Great. So now what? Well, now we can actually find the inverse function graph, at least. And remember, to find the graph of an inverse function, you just, you reflect it about the line y equals x. Basically, you swap x and y coordinates and flip the graph. So I'll try to do my best to show what happens for sine. But if this y-axis is now our x-axis and this x-axis is now our y-axis, what we'll get is basically the following curve. Now notice here, these swap. So what was the range now is now the domain, -1 to 1, and what was the domain, -π/2 to π/2, is now the range. Perfect, just like that. And you can kind of see why we need this restriction, because if we were to continue and do that whole thing, we'd get this weird wave going up and down like this, and that would fail the vertical line test. In other words, it wouldn't actually be a function. We want it to be a function so that you plug in a number and you get exactly one number out. So this is what's going to be our graph for y equals sine inverse of x. And often those parentheses are omitted, so I'll just try to get us used to that. So sine inverse of x like this, that's just the inverse function of sine. There is another phrasing here and the other phrasing is arc sine. It's kind of weird, but apparently, as history shows, this is kind of like a consequence of lack of technology at the time. Basically, when typewriters were a thing, it was difficult for people to write exponents, so essentially for writing papers and things, arc sine was a common notation. Nowadays, sine inverse is probably a little better for us, just because it's shorter. I'm going to use sine inverse. I'm never going to use arc sine, in fact. But the book tends to go in between the two, and in general, if you ever see arc sine, because it's still used in some places out there, believe it or not, you'll know what it means now. It's just another jargon for that. So now if we do the same thing here for cosine, we'll get the graph for cosine inverse, which again, you can also write this as arc sine, but I'm not going to use arc anymore. But again, arc sine, arc cosine, and even arc tangent are just the inverses of those. So arc just means inverse of that trig function. So here, if this y-axis and x-axis are now swapped, well, the graph is going to basically, so this is the positive y-axis, this will be the positive x-axis. So it should look something like, I want to get it right, it's going to look a little funny, but it'll look something like this. Perfect. Now remember, the range was -1 to 1, so that'll be the domain now. And, well, the domain was 0 to pi, so now that'll be the range. So 0 to pi. Perfect. There are, of course, a lot of consequences of introducing inverse trig functions, but before we get to those consequences, I want to show the similar thing we did here for sine and cosine, but now with tangent. We won't actually be doing the ones for the reciprocal functions cosecant, secant, and cotangent. They actually exist if you wanted to talk about inverses of those, but generally we just kind of abide by just these main three because they're just the reciprocals. So in fact, you can always manipulate an equation to make it involve sine, cosine, or tangent anyways, even if it involved cosecant, secant, or cotangent originally. So let's go ahead and take a look at the inverse function for tangent right now. Right, so now for a tangent, so this is the graph of tangent. Now remember that it has these vertical asymptotes, and of course we want it to pass the horizontal line test. Now notice one copy, one cycle that is, will be fine actually. It passes the horizontal line test. Once you have multiple copies, it fails. So what we're going to do is we're actually going to restrict the domain by erasing any copies of this one cycle of the graph of tangent. So notice in between its asymptotes would be its new restricted domain in order for it to be 1 to 1. Which is, of course, -pi/2 to pi/2. However, unlike with sine, these are open, not closed. And the reason why is because, well, you can't actually plug in -pi/2 or pi/2 into tangent. You would get undefined, which is why there are asymptotes there. Of course, what we saw with sine, they were closed because you could plug these in and you won't get undefined. In fact, sine has no vertical asymptotes in its graph at all. The range, well, the range is kind of funny, isn't it? The range is the set of all y values of this image, and of course it's from -infinity to infinity. So it's all real numbers, basically. And yes, if we look at the graph of the inverse function of tangent, given this restriction now, well, again, our y-axis becomes our x-axis, and then the graph gets flipped. So we basically get this image here. And there are, of course, now horizontal asymptotes opposed to vertical ones at y equals pi/2 and y equals -pi/2. So you can kind of see how the script flips, basically. And yeah, you can also see that the domain now is -infinity to infinity. So we indeed get a swap of these. All right, so now that we have that settled, we'll take a look at basically the main property that we'll be using in regards to inverse functions. And that, of course, is the cancellation properties. When you take f of f inverse or f inverse of f, you get back the same thing that you started with on the inside. There is a very, very, very subtle and big warning, actually, and it's this. This only works if y is in the range of f of x, of f, and when x is in the domain of f. So basically, these things need to make sense in order for it to actually work out. A really good example is a square root and a square function. Now, the square root is the inverse of x squared only when x is positive. Otherwise, you have a parabola and it'll fail the horizontal line test. So if you square root the square of 2, you'll just get 2. But if you square root the square of negative 2, the square root of the square of negative 2, you can actually just cancel these. Even though square root and square are inverses, they only really work when the inside of the square is positive. Since negative 2 is not positive, this actually doesn't really work out. In fact, if you were to do this just bit by bit, you get negative 2 squared is 4, and the square root of 4 is positive 2. So it's a little particular, actually. Now, I'll try to describe this the best I can, and again, it just kind of depends on what we're talking about and what makes sense. So let's take a look here. We want to take tangent of pi and then tangent inverse of that. Now, does tangent cancel with its inverse, and do you just get pi? The answer is no. And the reason why is because even though you can take tangent of pi, notice pi is not in the domain where tangent is 1 to 1, meaning that its inverse would not make sense there. Now, that's not to say that we can't actually evaluate this. We can, we just can't cancel straight up. So we'll actually have to be a little more careful here. Tangent of pi, if you recall, was, well, 0, because it's sine over cosine, and sine of pi is 0. So you get 0 over 1, basically, or negative 1. So that's 0. And now what is tangent inverse of 0? Well, tangent inverse of 0 is 0, because tangent of 0 will also give you 0. And 0 is actually in the domain negative pi over 2 to pi over 2. And we kind of see it right here. Here and here. So tangent inverse of 0 will give you 0. So the answer here isn't pi actually, it's 0, funny enough. So again, you have to be careful. Here, this one is actually, okay. In fact, this is really funny looking because it says cosine of cosine inverse of pi over 6. Pi over 6 technically is in the range of cosine. It just kind of sounds funny because, again, we're taking cosine inverse of pi over 6. Pi over 6, well, I think pi is about 3.14, so 3.14 over 6 is less than 1, and, well, the domain of cosine inverse is negative 1 to 1. So you can actually take cosine inverse of this. The only problem I see is that, well, I would imagine this should actually be radical 3 over 2 because cosine of pi over 6 is radical 3 over 2. So remember that cosine and sine, tangent, all of those trig functions, they take in angles and they output ratios. They output numbers. Here, this represents an angle. When we see pi over 6, we think of an angle. But if we're plugging it into cosine inverse doesn't take in angles, it takes in just ratio numbers. So coincidentally, this actually does work because pi over 6 is in the domain of cosine inverse. So we do actually get cancellation here, and the answer is indeed pi over 6. But just looking at it, it looks funny. It looks funny because pi over 6, we think of the angle pi over 6, when in reality we have to be cautious because when we take cosine, sine, or even tangent inverse of a number, we're not treating that inside as an angle anymore. Only for the non-inverse versions of those trig functions, we're plugging in angles. For the inverses, we're just plugging in numbers, and then we get angles as a result. I know that was a little technical, but we needed to see it somewhere. I think this was a good opportunity. So now we're going to take a look at a few other examples of evaluating cosine, sine, and tangent inverse of a number. Okay, so here I want to evaluate these three inverse trig functions, so let's take a look. So sine inverse of 1/2 basically means we're looking for an angle such that, so this basically says to find theta, let me leave some space here, such that sine of theta is 1/2. Now I needed to leave some space because there is a restriction on theta. This inverse function only makes sense when sine is 1 to 1. When is sine 1 to 1? What's our domain restriction? It's pi over 2 to, well, it's negative pi over 2 to pi over 2. So I'm going to write this, negative pi over 2 to pi over 2 interval. This symbol, by the way, epsilon, it just means is in, so theta is in that set. So we're looking for an angle such that sine is 1/2. Now we actually know in the first quadrant, when is sine 1/2? sine is 1/2 when theta is equal to pi over 6. So as it turns out, our answer is actually pi over 6. So this makes sense because sine of pi over 6 is 1/2, so sine inverse of 1/2 must be pi over 6. Another thing to consider is that, and very often people do this actually, if you take a look at the unit circle, from negative pi over 2 to pi over 2, it would be, well, the first and fourth quadrant, but seen like this. So I'm going to shade that region. So this is the domain here for sine. It's also the domain for tangent, but of course the domain for cosine, when it's 1-to-1, would be the top half here, quadrants 1 and 2. So this I think is pretty useful when it comes to evaluating these things. Let's see if we can do it for cosine. So we know cosine inverse of radical 3 over 2 without the negative would be, well, it would be pi over 6 because, so let me separate this. We know cosine of pi over 6 is radical 3 over 2. It's not negative though. But when is cosine negative in quadrant 1 and quadrant 2? Why do I say quadrant 1 and quadrant 2? Because that's when cosine inverse makes sense. That was our restriction on cosine for cosine to be 1-to-1. So, well, it can't be in the first quadrant, it would have to be in the second quadrant. Also recall that if we're going to get something that corresponds to an angle of pi over 6, that means pi over 6 must be its reference angle. In other words, what we have to find basically is a angle in quadrant 2 whose reference angle is pi over 6. And remember how that works for things in radians, you ignore the numerator. So it's going to be something over 6, something pi over 6. And it can't reduce. And it has to be in the second quadrant. So you can kind of count. 1 pi over 6, that's already this one. 2 over 6 reduces, 3 over 6 reduces, 4 over 6 reduces to 2 over 3. 5 pi over 6 doesn't reduce. And since 5 over 6 is less than 1, that means this is less than pi. So it's definitely going to be in the second quadrant. So this will actually be the value here. So this, believe it or not, is actually in the domain 0 to pi. Well, the domain for cosine anyways. But that's certainly in the range of cosine inverse. So that makes sense. Great. Now for tangent inverse, well, tangent inverse of -1, remember, for tangent, the domain for tangent to be 1-to-1 was the first and fourth quadrant of the unit circle, right here and here. So when is tangent negative? Well, it can't be negative in the first quadrant. Everything's positive in the first quadrant. So that means this angle has to be in the fourth quadrant. The other thing is that, remember, specifically what we're looking for, the range of tangent inverse is going to be in between negative pi over 2 and pi over 2. So even though we think of things in the fourth quadrant to be kind of large angles in radians, so think of like 11 pi over 6, for instance, or let's say, 7 pi over 4. But the problem there is that even though those are actually in the fourth quadrant of the unit circle, well, they won't be in this interval here. So you have to be kind of careful. Now also notice, so something that comes to mind here is if you think of 1, well, I know that tangent of pi over 4 is equal to 1. Okay? So if you look at this unit circle, where this angle is pi over 4, tangent of pi over 4 is 1. So it's going to be an over 4 because of the reference angle idea. And furthermore, it actually has no choice but to be this angle, which is negative pi over 4. Now, yes, normally we don't view it like this because we're kind of used to doing it the normal way where the angle increases from 0 to 2 pi. But if you swing back around, well, we have the notion actually of negative angles. So it still makes sense, we're just maybe not used to it. So in actuality, tangent inverse of -1 must be equal to negative pi over 4 because tangent of negative pi over 4 will give you -1. And it also actually really helps that tangent is an odd function, meaning the negative comes out. So if you take tangent of negative pi over 4, it's negative tangent of pi over 4, which is -1. So now we'll move on to these examples here. Now to start off these problems, the first idea that I want to give you is that, remember that an inverse function will output an angle. So we often think of this as an angle theta. So just kind of keep that idea in mind. So with that said, we can actually find out what this is, because remember that, well, sine of what is radical 2 over 2? If you look back at our tables that we've seen before, well, recall that sine of pi over 4 is radical 2 over 2. And this is indeed in the interval where sine is 1 to 1, negative pi over 2 to pi over 2. So this is actually pi over 4. And then from there, we can just replace it and say that this is just equal to tangent of pi over 4, which we know is 1, kind of like we just mentioned from the previous example. The other way we can do this, though, just kind of hear me out, is if we don't know it's pi over 4, but we just say it's an angle, then, well, just imagine that's theta. Then we can say sine of theta is radical 2 over 2, and we can actually create a right triangle with angle theta. And since sine is opposite over hypotenuse, and we have sine of this angle theta is radical 2 over 2, we can take the top part of the fraction to be the opposite side of a triangle, and the bottom to be, so the denominator of this fraction, to be the hypotenuse side of a right triangle with the angle theta in mind. So this is radical 2 over 2 like this. And then from here, you can use Pythagorean Theorem to find the remaining side, and of course it's going to be radical 2 as well, as it turns out, because this angle really is pi over 4 all along. And then if you want to find tangent of this angle theta, notice tangent's opposite over adjacent, so we just get radical 2 over radical 2, which is indeed 1. But in doing this, we actually didn't even find pi over 4, which is interesting. So that gave you two ways of doing that. For this second example here, there's actually only really one way of doing it to get the exact value. And the reason why that is well, and it has to do with the fact that tangent inverse of 2 isn't actually a value we know. So we're not going to find tangent inverse of 2, we're going to bypass that. So we're just going to call this theta, and we want to find cosine of theta. But before we find cosine of theta, so let me just write this is equal to cosine of theta with that in mind. What this tells us, so I can write it over here, if tangent inverse of 2 is equal to theta, well, if you take tangent of both sides, tangent of this side equals tangent of that side, like this, here these cancel because 2 is indeed in the well, it's in the domain of tangent inverse. So these cancel, so we get this. We get tangent of theta is equal to 2. Now, much like what we try to do over here and create the right triangle, it's a little harder because 2 isn't a fraction, but you can always make it a fraction, of course. So I'm going to write it as 2 over 1. Perfect. So now let's create a right triangle with angle theta. And all we know about this right triangle is that its tangent ratio will be 2. In other words, we're going to treat the numerator as the opposite side and the denominator as the adjacent side, of course, because tangent is opposite over adjacent. So this is going to be 2 over 1 like this. And can we find the remaining side? We certainly can using Pythagorean Theorem. Notice 2 squared plus 1 squared is 5. So this is going to be the square root of 5, so that when you square it, you get 5. Kind of did that quickly, but you can verify that on your own. And finally, now we want to find what? We want to find cosine of theta. So we can do that actually. Cosine of theta is adjacent over hypotenuse. So that means cosine of the angle theta is 1 over radical 5. And if you rationalize, of course, this is just radical 5 over 5. I didn't actually show the work of rationalizing, but we're just multiplying top and bottom by radical 5. And that's what we get. Kind of similar to how you get radical 2 over 2. But in any event, that was it for that. And in fact, that'll be the end for 6.6. It's all I wanted to talk about really. In fact, this actually ends our discussion on chapter 6 in general. So I'll see you in the next videos for chapter 7. It's going to be pretty interesting, just like chapter 6 has been. It's actually going to be a little more specific because we're going to be talking about still trig functions. In fact, chapter 6 is just getting us used to things. Now we're going to take it to a little bit of the next level and look at all sorts of different identities and how we can manipulate certain trig functions and equations as well, actually. So it's gonna be interesting. It's gonna be a lot of fun. I'll see you in the next videos for that. Thanks for watching. See you then.